The inner part of the adrenal gland, the adrenal medulla, was an extension of your sympathetic nervous system, right? It was the part that released epi and norepi when you're in fight or flight mode. But the outer portion of the adrenal gland, the adrenal cortex, made steroid hormones that are primarily released in response to stress, like cortisol. So sometimes you'll hear cortisone referred to as a corticosteroid. Have people heard that term before, corticosteroids? When they talk about corticosteroids, they're talking about compounds that not come from the cerebral cortex, but from the adrenal cortex. They're called corticosteroids because they're steroid-based compounds. Steroids have that 4-ring structure. So glucocorticoids, like cortisone, stimulate the process of lipolysis, releasing fatty acids, hopefully that you'll be able to burn for fuels. But I did mention the clinical application. Let's see. I'm not going to go over all this because it's a 109 topic, but I just want to refresh part of it here because there's so much clinical relevance to this. Hypothalamus releases corticotropic releasing hormone that stimulates the anterior pituitary to release adrenocorticotropic hormone, ACTH. And ACTH is what stimulates the adrenal cortex to release corticosteroids. The most common one that people know is cortisol, cortisone, that help you to save sugar. It is considered to be glucose sparing, which is why you're going to be releasing it if you are in that when you're in that post-absorptive state. Because when you're in that post-absorptive, is there plenty of sugar or are you kind of running low on sugar in that post-absorptive? You're running low on sugar. And what organs absolutely need as much sugar as they can get?
Brain.
Right? Brain, spinal cord. So you want to save as much sugar for your brain and spinal cord as you can and make other types of nutrients available for everybody else to use. And so the cortisol has these metabolic effects. And I'm bringing this up right now because you already may be familiar with in 109 that high levels of cortisone and other similar compounds suppress immune system response. We talked about this a little bit when we did the immune system. And there are many conditions where you're going to want to suppress inflammation in your patients. We mentioned a little inflammation leads to healing, all right? A little bit of acute inflammation leads to healing. But chronic inflammation especially, that's not leading to healing, that's primarily what you want to do. So if you've got a patient, for example, that's got bursitis, inflammation of one of these bursa sacs or tendinitis, you might want to treat them with a steroid similar to cortisone. Or somebody has an autoimmune disease like rheumatoid arthritis, an example. You might need to treat that with a much stronger type of steroid like prednisone. And prednisone is like the mother of all of these steroid kind of compounds, similar to cortisone, but just much more potent. And the reason I'm bringing this up now is that people who are on long-term stress of this year, all right, are going to throw off this axis, all right? And if you look at the medications that come along with your prednisone or other kind of steroid that you take, that almost all have this ONA ending. You're going to see them talk about worries about the HPA axis here. Because high levels of it over time, we mentioned, will cause something like Cushing's syndrome. So in Cushing's syndrome, with too much of this cortisone, again, we are liberating fats, right? It's the cortisone is causing lipolysis. But if you are not able to burn the fats that are being liberated, you redeposit them in different locations. And that's what you're seeing in people that have Cushing's syndrome, which is a hypersecretion of cortisone or common thing. You see, this is a very typical sort of presentation. This is a relatively large one here. They call it a buffalo hump when you see the fat deposit sort of between the shoulder blades in the back here. You get more in the face too, so they get like this moon face here. There are other things that go along with it, but those are generally the things that you're going to pick up on sort of the fastest. You see somebody with that hump, they've got some sort of problem with their HPA axis here. Okay, so that was the glucocorticoids. So would glucocorticoids be released when you are in the absorptive or post-absorptive? Post-absorptive. Does it make sense they'd be post-absorptive because they're trying to stimulate the breakdown of lipids?
Yes.
So that you're using that as a fuel. And by the way, what organ is secreting both insulin and glucagon? Pancreas. Pancreas. All right, a little bit about this energy content in food here. Starting with the term that you've probably come across already a lot, which is a calorie. And there's actually a problem with your study guide that has you little fill in the blanks on this end because they kind of, I'm sorry, it's messed up on your little study guide. I will explain why that's a little bit messed up. So calorie is a measure of heat energy. It's a measure of energy. And a little c calorie refers to the amount of energy that it would take to just raise 1 gram of water, that would be 1 cc1, 1 gram of water, just 1 degree Celsius. It's the definition that we give. That would be what a little, and that is just a tiny amount of energy. What most people, they talk about like a candy bar having 120 calories or something, they're really talking about a kilocalorie. And you will see an uppercase C referring to a kilocalorie, which is a lot more. A kilogram of water instead of a gram. How much is a kilogram? What does that prefix kilo refer to?
1,000.
1,000, right? Deci would refer to deci.
Deci?
Centa would be
100.
100. Deci is just 10.
10.
Kilo,
1,000.
1,000. So notice here the different sort of calories in different foods. Proteins, carbs, fats. We want to really focus on the difference between fats and carbs. Why is there the difference?
Between what?
Why is there so much difference in the calories between carbs and fats?
Because carbs break down.
Fats you like burn off.
Yeah, because carbs break.
Because fat is for long-term, no, but that's not it. I'm sorry.
No.
It's, you know what, I appreciate the attempts. I'd rather people make attempts at this thing here.
It's okay if you're not
But
right.
here's the thing. Carbohydrates.
It's longer.
Carbohydrates are like sugars. C6, H what?
12,
12, O,
6.
6, right? So, and carbon has the atomic weight of what? You haven't memorized your periodic table of the elements here?
Oh my God.
12, 8.
12, good,
Four,
very good.
12,
Atomic weight of 12. Hydrogen, only each one.
One.
Oxygen,
6, 4.
16.
just random numbers.
16.
This round's a random number. 16. 16. I'm not.
Yeah, pretty much their number.
Which of these
Yes,
elements,
I don't know.
which of these elements is almost completely lacking in lipids?
Oxygen.
The oxygen.
Is that what
Because
you
lipids are basically just long chains of carbon and hydrogen. They'll often just refer to them as hydrocarbons. And where's the energy stored? In the hydrogens. So because carbs have a lot of oxygen by weight, all right, are these electrons carrying energy that we're going to extract? No. All right? So we basically have a lot of wasted weight here, if you will. Whereas lipids are nothing but pure carbon and hydrogen. So by weight, lipids have twice the hydrogen that the same weight of carb would have. What did I say? I have no idea what I just said. Oh, okay. I said that lipids have twice the amount of hydrogen by weight. Because they don't have all that wasted weight from the oxygen that carbs have. And so this is why, again, lipids have twice the amount of caloric value. Now, I also mentioned something the other day is that another reason that your body likes to store long-term energy as lipids is because they're hydrophobic. Did we have this conversation? I thought we had this conversation.
Yes.
When you store carbs, for every 1 pound, I'm not going to expect you to know the number, but for every 1 pound of carb that you store, 3 pounds of water get drawn along with it. That's how hydrophilic the carbs are, extremely hydrophilic. Small ones like glucose dissolve very easily. The big ones like glycogen, they just suck water to them. And so when you store 1 pound of carb, you're basically storing 4 pounds. 1 pound of the carb plus 3 pounds of the water that get dragged along with it. So for example, again, 1 pound of, you think, oh, 1 pound of, 1 pound of fat. Well, the caloric value of carbs, you'd have to have how much carb? Basically twice as much, right? So you need 2 pounds of carb. But that 2 pounds of carb would bring along with it how much water? 6, right? Basically about a 1 to 3. So you'd also have, what, 6 pounds of what? So what would you rather have to drag around? 1 pound of fat or 8 pounds of carb and water? Yeah, I know. Next time I'm looking down, it's like, well, it's still better than having 8 pounds of carb and water. Now this is just your basic sort of energy balance, because energy consumption versus expenditure, we're talking about a balance sheet here, right? If you're consuming more foods than you're burning, you're gonna end up storing the extra ones primarily as adipose tissue. And about half your adipose, I don't know if we mentioned, about half your adipose is subcutaneous. About the other half is internal. Those numbers change when you age. When you're when you're a young baby, when you're a little baby, a much greater percentage of your adipose tissue is subcutaneous. When you reach your golden senile years, it becomes internalized. If you've dealt with babies and you've dealt with geriatrics, you can probably relate to that a little bit. You see a little baby, my little nephew Zach. Look at his little fingers. Look at his little 6-month-old fingers. How do they look? They're all puffy, right? Like little sausages, right? Why? Because of all that extra. That's all subcutaneous, right? Is that way my Aunt Ruth's fingers are going to look? My great Aunt Ruth?
No.
Are they going to look like bony, kind of witchy kind of fingers?
Witchy.
Yes, all right. Again, because of that change in fat distribution.
I mean, you're not a baby, so.
But again, if you expend more energy than you consume, then you're going to lose weight here. It sounds really simple, doesn't it? Oh, to lose weight, you just have to eat less than you actually burn. Problem solved. Yeah. What regulates it, very complicated. There's a lot of things that go into it. Social, psychological pressures. All right. Dietary habits are important. Access to the refrigerator so that you can eat your feelings. Very important.
Know that too well.
Not that anybody knows anything about that, yes, of course. So there are different factors here. There are some importance maybe of stretch receptors, especially along the digestive tract in the stomach. Seems like stretch of the stomach has an impact on making you feel full. All right. People that have weight reduction surgery, like a gastric sleeve, the bypass where they basically take off most of your stomach. All right, like a gastric sleeve. Because there's little of the stomach, it's going to fill much faster. And they're going to feel not only the stomach, but because it's going to stretch, they're going to feel full a lot sooner, a lot faster.
I see that a lot in the TV shows, My 600-Pound Life. They always do that.
Yeah.
Well, my
uncle got one.
My
And his stomach was like this big.
Oh, wow.
When they took that out.
Yeah, I had a picture of it. Yeah, it looked like a little alien.
How long ago did you have this procedure?
How long ago? A couple months ago.
Okay, that's pretty recent then.
Yeah. He definitely lost a lot of weight after it. He can't really eat like he used to.
Right, you just eat a little bit and it's like,
Yeah.
When he got gastric bypass, my cousin got that, she gained all the weight back. That's not funny, but it was like a few years ago, she like got it, and then she gained all of that. I was like, my goodness, wow. Okay.
it will happen. And people is like, I know my stomach is full, but I'm going to keep eating anyways, all right? And you stretch it basically back out. Your stomach is plastic that way. It adapts. Smooth muscle is very adaptable to the stresses that are put on it. And so if you keep over time, he's gonna stretch that stomach back to its.
Is that where the stomach ache comes from? If you like stretch on your stomach too much, or?
Don't think that's where stomach ache comes from the stretching.
Okay.
Don't believe so, but I could just be making this up. So where are we going with this one in here? Couple of things that you should know. CCK does seem to have some ability to suppress appetite. Have we come across CCK before? Yeah. CCK was released from the intestines in response to a lot of digested foods coming down, especially partially digested lipids and proteins. It was the hormone that triggered the pancreas to secrete all the digestive enzymes, right? It was the hormone that triggered your gallbladder to contract to release the bile into the duodenum too. But it also seems that same CCK tends to decrease appetite, or at least suppress appetite somewhat here.
So in this case, it's the decreased appetite?
Yes. These first two ones, CCK, and this is a relatively new hormone that is discovered called leptin, which is a hormone that's released from adipose cells that also tend to suppress appetite. It's released during the absorptive state. The last one that's mentioned here, ghrelin, leads to the stomach, and it's a compound that actually seems to increase appetite. But there's a lot of interplay between this, so it's not quite as simple. Because ideally, it would seem like if you could come up with a drug that would decrease levels of ghrelin and increase levels of leptin, then you would think that that would help to suppress your appetite and help in a weight loss regime, right? Does that make sense? Do you think people are working on that like nonstop in some labs right now? Absolutely, all right? Is there a lot, if they figure out this solution here, is there a lot of coin to be made by this? Cha-ching, cha-ching. Which tells you how challenging this is to control appetite. There's so many factors that are involved with this. But despite the fact that people are working on this around the clock, they still haven't come up with a good anorectic medication. Anorectic would be something that would suppress appetite. Do people know that term, anorectic? Or when they talk about somebody who's anorectic and anorexic, they're people who do not have appetite, they're not eating. When they talk about a drug that suppresses appetite, they refer to that as an anorectic drug here. Okay.
That's it, it's all down to.
I mean, this is where we end up here. When we talk about energy expenditure, we start with what's called just your basic metabolic rate. Basal metabolic rate just refers to the amount of rest that you would be, or amount of energy you're spending with virtually no activity.
Resting energy.
Now, there are ways of actually directly measuring this if you are in a scientific sort of setting, especially like a university research setting on it here. You would actually be able to measure basal metabolic rate by measuring different types of gases. Especially, what gas would you be measuring?
Carbon dioxide.
Primarily carbon dioxide levels. Because since there's virtually none in the atmosphere, all right, when you're breathing out through this, this machine here, they don't have to worry about how much of the carbon dioxide is from the atmosphere, how much is from cellular respiration. It's all coming from cellular respiration. And so they could use that to more accurately determine what your resting metabolic rate, your basal metabolic rate would be. Now, because that requires sort of more advanced equipment, and sort of an intermediate way, if you really want to get a more accurate measurement, is to sort of measure the amount of thyroid hormone. Because thyroxins, T3 and T4, are the primary hormones that have an impact on your metabolism.
T3 and T4.
T3, T4.
T3.
Would people with hypothyroidism tend to gain weight or lose weight? Hypothyroidism means you're not producing. What does that prefix hypo mean? Hypo means lower, below, right? Because where do you stick a hypodermic needle?
Beneath the dermis.
Below the dermis, right? Hypodermic needle. Hypo meaning under or below. Where a child that is hyperactive is overactive. So hyperthyroidism is different than hypothyroidism. Got to listen for the vowels. So a patient of yours that had hypothyroidism, would they tend to gain weight or lose weight?
Gain weight.
They would tend to gain weight if you have hypothyroidism. And that's usually what they're doing the assay for people that are coming in with weight problems. Before worrying about other kind of treatments like gastric sleeve, they would probably first do an assay to see, well, maybe there's a hormonal issue here. Maybe you are slightly hypothyroidism, have some hypothyroidism, because then you can treat it with thyroid medication. What about people on the other end, like people with Graves' disease, like hyperthyroidism?
They lose.
They would tend to
lose.
lose weight. So the importance that one would take away from this here is that when people have thyroid assays done, it's almost always because they're having symptomatic issues with weight or things associated with the thyroid hormone, because, follow me with this also, right? Thyroid hormone increases your metabolism, correct?
Yes.
That's what I know, right? What will that do to heat production?
Increases.
Increase heat production, right? So will people with hyperthyroidism, will they tend to feel too abnormally hot or abnormally cold?
Cold.
They're gonna feel hot, they're gonna feel warm, hot to the touch. That tends to be one of the signs that comes along with hyperthyroidism. Is it hot in here? Is it just me thinking they're having a hot flash or something, issue like that? Where on the other hand, people with hypothyroidism are gonna tend to feel what? Cold. That's something that comes along with it. It's like, I'm always cold. I'll just put a jacket on. I always feel too cold. So if you have a patient that's coming with those symptoms, all right, that's got weight issues, all right, and also having those kind of temperature issues, you might want to do an assay for thyroxine on that patient to see if that patient does have a thyroid issue or if there are other things in play. I think that's all I wanted to talk about with metabolism.
So you said the thyroid hormone increases appetite?
Increase the
Oh,
metabolism.
metabolism, okay.
I think that's all. This is all I want to really cover on metabolism. I could start on the urinary system, but ooh, people are giving me the stink eye. Okay.
Ready to write. I thought you were gonna say something important.
I think it's the same.
No, it's not.
You thought I was going to say something important?
Yes, I don't know what it does.
Excuse me here.
What's the other slide?
What's what?
What's the other tab? Is it the same? The first and the second one? Are they both metabolism?
The very top.
Yeah,
But-
they're both
The very
metabolism.
The top tab.
The left.
The
The top
PDF
tab?
where it says PDF.
Airman.
Those two.
Yeah.
Yeah, are they the same?
Yeah.
Oh.
Oh, no. This is actually one, sorry, this is a different one here. This just goes in, has everything the other one does, but it just goes in a lot more detail about cellular metabolism.
Do we need to know that?
Well, you need to know some of the stuff from this. Let me tell you what you needed to know from this. You do need to know some of the stuff from here that we've already talked about. So, for example, we talked about, this goes into more detail, for example, about glycolysis. But it just gives you more than you need for the test.
Oh, okay, no.
It just tells you this. Could you pick out something from glycolysis? We get what's our end products of glycolysis?
218. Oh.
Our what?
2 per.
Pyruvates, 2 pyruvates that are 3 carbon sugars, right?
Yes.
All right. What else do we get from this process? How many ATPs net gain?
2.
2 net gain, right? Do we have to waste 2 to begin?
Yes.
We waste 2, we get 4, so the net gain was
2.
2. All right. If we're breaking the frame apart, which we are, do we also have to remove hydrogens?
Yes.
And so that's why you're seeing from each of the little 3-carbon sugars, we remove hydrogen in the form of what? NADH. So that's what they're showing here, just in more detail. And they're showing each of the enzymes that are involved in this step. Do you want to know each of the enzymes involved? I don't think so.
Is this in our canvas?
This is not on campus
Oh,
here.
okay, that's all.
These pictures are in your lab and in your textbook.
Okay.
This is all in your textbook if you want more detail about how this works. This is not on the PDF file that you have. And then it goes into more detail about what happens in the mitochondria that we take our pyruvate, our 3-carbon sugar, all right, and then break it down into a 2-carbon sugar that we attach a coenzyme A to produce acetyl-CoA. But of course, in the process of breaking it down, we also have to harvest off hydrogens in the form of NAD, forming NADH. So it's just a review of what we've already done. And then of course, the process of the Krebs cycle,
Oh,
the chop shop.
yeah.
What's our entry into the Krebs cycle? The citric acid cycle. That's the test question. Acetyl-CoA. So acetyl-CoA is going to provide our entry. We attach it to a 4-carbon sugar, producing a 6-carbon that was called citric acid. How do we get back to our starting point? We've got our 6-carbon that we start with. We've got to get back to our 4-carbon that we attached it to. So during each turn, we have to get rid of how many carbons? 2 in the form of? Carbon always comes in the form of carbon dioxide. And that's what they're trying to show here. If you look carefully, you can find carbon dioxides being removed.
It's on the inside of the circle.
Yeah. You can see the carbon dioxide being removed. You can also see us harvesting off the hydrogens in the form of what? NADH. 1 in the form of this second rate FADH. And then that gets us back to our starting compound. What do we do with all the NADHs and FADHs? Oxidative phosphorylation. What organ does that occur in? I'm sorry, what organelle? Did I say what organ? What organelle? Mitochondria. Oxidative. Where did substrate level phosphorylation take place? Just outside, and that means in the cytoplasm someplace, just in the cytoplasm, cytosol. So when we get ATP from glycolysis, that's outside, that would be substrate level. The example I gave, like when you donate a phosphate from creatine phosphate to regenerate ATP, when your muscles are working really quickly, that would also be outside the mitochondria. But the key thing about this process of the electron transport system is that we're going to use the energy of those electrons to pump hydrogens against their gradient. We use the energy of the electrons to pump what?
Hydrogen.
Hydrogens. And then we allow the hydrogens to flow through the critical molecule that's called ATP synthase. And the name is great, ATP synthase. Tells you it's making what? ATP. What powers ATP synthase? The flow of hydrogen. What powers ATP synthase? The flow of hydrogens. We expend energy to pump the hydrogens into the space, and then we let it flow out through what molecule?
ATP.
ATP synthase.
Synthase. Flow of hydrogen.
And there's a 1-to-1 ratio of flow of hydrogens to the ATP that are generated. Every hydrogen that flows through it provides enough energy to regenerate an ATP. NADH had enough energy to go to 3 of these proteins, each one pumping a hydrogen. So NADH pumped 3 hydrogens, 1, 2, 3, across the membrane, so that the exchange value, if you will, for NADH is worth how many ATPs?
3.
They're showing that FADH, sort of the second rate carrier, only pumps how many? 2, which means it's only good for
2
2.
ATP.
And that's all they're trying to show in here. And by the way, this process, for people who take general biology, this process is occurring inside of chloroplasts too. We see something almost identical in the formation of ATP that's used for driven photosynthesis, and nobody really cares. Okay, that's fine. Each NADH generates 3, FADH generates 2. And again, the net yield was about 36. It's good to know that, yeah. The easiest way to do that is keep in mind that
So it's 36.
about 36 to 38, 36 is probably what I put on a test around that number here.
Is 36 like the neck? I mean, including
Would be the
2
total
necks?
gain rate.
So like 38 would be the, not the net?
No.
36.
Like, how do you get to 38?
There's debate that can change because remember that we talked about how we have to take our pyruvate and things like this into the mitochondria. And in some areas it seems like it uses up a little bit of ATP to do that. In other cases, it doesn't seem like it takes an ATP. That's where we get the 36 to 38.
Are you gonna put 36 on
I'll
the
put
example?
36.
Okay, perfect. So 36.
I'm not going to do something super evil, like have 36 as one choice and 38 as another choice.
Right.
That would be like extremely evil, even for me. The detractors would be things like 3, 12, 36, the correct answer, 51, 57. 57, that's Heinz. 50, that's a whole different sort of thing.
You said the entry to citric acid cycle is acetyl-CoA.
Acetyl-CoA, yeah.
I can see you putting a question like that and then you put acetyl-CoA and acetylcholine. I would be so dumb to choose acetylcholine first
No.
and then I would erase it because they sound alike in my head. I can see myself doing that.
I know you all think that I intentionally try to come up with evil, tricky sort of questions. I know you all think that because that's what I thought when I was a student. I was sure that my professor up at thinking, oh, they'll never get this one here. Oh, they'll never get this one here.
So is this payback? No.
Super here, they'll never. But it's just because we're stupid and we don't realize that our questions aren't that clear. But again, about the 36 years, the easiest way to sort of keep in mind that a sugar molecule, C6H what?
12.
And almost all the hydrogens are going to be shuttled over by NADH.
Which is 3.
And
So
since
multiply.
each NADH is worth how many?
3.
3. 3 times 12 gives you
36.
36. Okay. Well, now that's it.
This was such a fun class today.
It was a fun class today. How did that happen?
Like,